Hello and good day, Geometry. With you to go over math packet number 7, introduce the questions to you, get you all the formulas you might need, and a little bit of explanation as to what I expect. The due date for math packet number 7 is February 16th. So today is the 5th, so you still got just under 2 weeks for that. And this first logic question, on the surface, ooh, boy, whole bunch of shapes here, right? Not a whole lot of words, not a whole lot of given information. Or is there? Okay. In class, we kind of talked about this question being like coding, okay, to where you are presenting a rule, and then that rule gets followed throughout the program, right? And the first kind of rule that we're given here is that a square and a triangle make 7. So what you're looking for is, what kind of relationship would a square and a triangle have that together would give us a value of 7? And we discovered that, well, if you look at a square having 4 sides here and a triangle having 3 sides here, 4 and 3 do make 7. Of course, we're used to when things are right next to each other in algebra, it means that we're multiplying. But it seems here that when the square and the triangle are right next to each other, we're adding. Okay, so that's what we can conclude based on that rule there, that information. That the rule is side lengths have something to do with it, and 2 shapes next to each other means that we're adding. Then we'll go down to the next row, where we're given a little bit more information. It says a triangle within a triangle is 27, and a triangle within a square is 81. Okay, and we looked at this, and we can conclude that the rule of side lengths is going to continue here. So we've got a triangle within a triangle, each with 3 side lengths. Then we have a triangle in a square, and the only difference between these 2 figures is that the first one, the triangle is inside of a larger triangle. And the second one, that triangle is inside a larger square. So something about moving from a triangle to a square causes the value to increase from 27 to 81. And the question, of course, is, what's going on here? And so we talked about how can you get from a 3 and a 3, because you got 3 side lengths for each triangle there, a 3 and a 3 to make 27. And then a 3 and 4 to make 81. And we discovered that, well, it must mean a triangle inside of a triangle is 3 to the 3rd power, which equals 27. And a triangle inside of a square is 3 to the 4th power, which is 81. So the information that we've been able to gather here is that side lengths kind of give us our numbers. 2 shapes next to each other mean that we're adding them. Or 2 figures, I should say. A figure inside of another means that we're using exponents. And from all that information, we are now asked to put that together in this situation to come up with the answer. Okay, so it's using the previous rules now in kind of a new situation to come up with a value. And that's what you're doing for this one here. Right? Next one. Emily has a rectangular vegetable garden with a 20-foot length and a 12-foot width. Whenever I have the opportunity to draw something, I always like to take it. That way we're not looking back up into the question, what's the length again? What's the width again? It's here for us. So we got a rectangular garden, 20-foot length and 12-foot width. Okay. She increases the garden's length by 40% and its width by 25%. What is the percent increase in the garden's area? So now we have the second garden, which is going to be bigger than the first. Okay. And how we got it to be bigger was by increasing the length by 40%. And we talked about, what's that calculation that allows us to increase a value by a percent? And there were a couple different ones that were tossed out there, all of which were correct. And we decided that the most efficient was to multiply our length 20 by 1.40 or just 1.4. Okay, and why that increases 20 by 40%? Multiplying 20 by 1 here, the 1 and 1.4 doesn't change the value, right? That gives us our original 20. And then multiplying by an additional 0.4 there gives us the increase of 40%. Okay. Other people talked about, well, you can find 40% of 20 and then add that on to 20. Yes, that works also, but multiplying by 1.4 kind of takes care of that for us. It's the most efficient way to increase 20 by 40%. So then increasing the width by 25%, we said, well, we're going to multiply that by 1 to get my original 12, and then an additional 0.25 or 25%. And that is going to give us the new length and the new width, which I believe we said was 28 here, and this was 16, 15. Sorry. Okay. So the values of our new garden are 28 by 15. So then we said the ultimate question here: what is the percent increase in the garden's area? That is not asking you to just simply find the difference between the areas. Okay, just subtract the areas and that's your answer. We're looking for a percent of increase. A formula for a percent of increase is difference divided by original. So you do need to find the area of the original garden. You do need to find the area of the new garden here. You will be subtracting those to get the difference, but then that next step is to then divide by the original garden's area. How you can tell which value is the original? It's the one that came first before an increase. Okay, so the original garden, that first garden's area, is the value of the original in that formula there. Okay, percent of increase, the difference between the values, the difference between the areas, divided by the original area. 5-card challenge. Not much to say about this that you don't already know. Of course, you do have an ace. We love aces because they allow us to not change the value of a number and get, extra points. Multiplying by 1, dividing by 1, using taking some of the power of 1. All of those things allow you to write new equations and not change the value. So that's a nice gift for you there. Next page, we have the area of the shaded region, which is the red section here. And we looked at this shape, and we've got this circle with this little extra piece sticking off the end there. Okay, and it actually turns out that the hardest part of this question is finding the area of the entire figure. Okay, which includes everything in the circle and then everything inside that square. And we know it's a square because we are told that the radius of the circle is 12. So if you label each of those radiuses 12, we see that we've got a square. Okay, a 12 by 12 square. So we talked about, okay, how can we use that information to get the area of the entire figure? Well, different ideas were tossed out there, but most efficiently, we said, well, let's find the area of the square, and then subtract the area of the circle that remains. Okay? Not sure what happened there, but find the area of the circle that remains with that square removed. And of course, the area of a square is base times height, right? But the area of that section of the circle, realizing that it's 3/4 of a circle, we're going to take our formula for the area of an entire circle, and we'll be taking 3/4 of that. So you can either multiply that value by 3/4, or another formula you could use is using 3/4 as a decimal and multiplying pi r squared by 0.75. Okay, we've worked with semicircles before where we had to divide the area of a circle by 2 to get that semicircle. Here we want 3/4 of it, so we're going to multiply by 3/4 or multiply by 0.75. Okay, and that will give us the area of the entire figure. Then to find the area of the shaded region, well, since this segment here goes directly from one corner of the square to the other, it divides it in half, which means that you got your red shaded section here, but then this section, this red shaded section is the same size as that white section there. And so you realize, oh, okay, that red shaded section is really just half the area of the square. And you can get your percentage of the shaded region by taking part divided by whole, which for our purposes is the shaded area divided by the whole area. Okay? All right. Moving on. Here we have our pattern block figure. We've got 4 squares that are given to you. We talked about this in algebra, and you know we got 1 yellow square in all of them, so that's pretty handy. And then we went to the total blocks column, realizing that you know we've got 4 squares here. The first one's a 1 by 1 square, which is 1 block total. Then we have a 3 by 3 square, which is 9. A 5 by 5 square, 25 total blocks there. And then 7 by 7, 49 total blocks there. And we saw that this pattern of that these being perfect squares, 1 is equal to 1 squared, 9 is equal to 3 squared, 25 is equal to 5 squared, 49 is equal to 7 squared. And then we were able to easily get the red block column by just subtracting 1 from the total to account for that 1 yellow block. Okay, and then we predicted the next row, you know, this would be 9 squared following the pattern, which is 81 total blocks minus the 1 yellow gives us 80 red, and so on and so forth. For geometry, I'm not having you make a graph for this one. You need to complete the table and then write 2 expressions, one that represents the number of red blocks in each figure, and the one that represents the number of total blocks in each figure. And your expression the goal it should accomplish, the purpose that it serves, is that if I ask you for the number of total blocks in the 20th figure, rather than having to complete this table all the way down to figure 20 to answer that, you should be able to plug 20 into your formula, into your expression, and the answer should be the number of total blocks in that figure. So for example, if we had a pattern where we had, well, let's use x and y, because it essentially is a function table here, where x was 1, y is 3, x is 2, y is 4, x is 3, y is 5. And I said, you know, write an expression that will tell me, you know, what the output is, what the y value is for any given x value. And you would write that y equals x plus 2. Because that's the pattern. That's how we get from x to y. So if I asked you, you know, what's the value for y when x is 20, rather than having to continue this table all the way down to x equals 20, you can just take that 20, plug it into your expression, plug it in your equation here, and you would get, oh, y is 22. That's what I'm asking you to do here. Give me an expression that will allow me to ask you for the total blocks in any figure, any numbered figure. You plug that in, and the result will be the number of total blocks. And then same thing for the number of red. This is a bit of a challenge. Okay, I'm not going to sugarcoat it, not going to lie here. This is a bit of a challenge. So if you need help, please do come and see me. But play around with it a little bit. Okay, the figure number. How does the figure number relate to the number of total blocks and red blocks in the pattern? Then we move to surface area. In algebra, we talked about this, the net of the figure. Kind of looks something like 4 leaves here, right? Because it's widest at the middle. That's why these leaves connect, and then it kind of tapers off as you go up towards the top of the sphere and down towards the bottom. So the formula for the surface area of a sphere is 4 pi r squared. And then your job would be to calculate the surface area. If you do this in your algebra packet, then make sure in the geometry packet you write C algebra, okay? Or if you do it here, then your algebra packet, write C geometry. If you just leave the page blank, I'm going to have to take points off because that kind of tells me that you didn't do it. Okay, so make sure that you give me something to let me know where your answer for this question is. On to volume. We again filled this out in algebra. The formula for the volume of a sphere is 4/3 pi r cubed, or another way to write that is 4 pi r cubed divided by 3. And so the calculation for this particular sphere, I'll just use the second formula there, is 4 pi times 9 cubed divided by 3. And what that, I've written this volume several times now, but I can't remember exactly what it is. Let's see, divided by 3, 3053.63. And I think other people got answers of 3052 and something. That's fine. You know, it kind of depends on whether you use the exact value for pi by pushing the button pi button on your calculator, or if you are using 3.14. So if you're off by 1, that's fine. If you're off by 10, even 10, that's more of a problem. Maybe you rounded pi to 3.1 or just use 3, okay? The kind of standard value that of pi that is used is 3.14. So you should use that as well. Your question here, geometry. The diameter of the sphere, first of all, let's underline that because that's important. The diameter of the sphere is increased by 33%. So kind of back to Emily's garden, we have an increase by a percentage here, okay? So you're going to take that diameter and you're going to multiply it by 1.33, or if you want to be more accurate, the fraction value would be 4/3 to get the new diameter of this larger sphere, okay? Once you get that new diameter, you're going to use it to find the area of the new sphere and then calculate the percent of increase, which, remember, again, back to that garden question, the formula is difference divided by original. So once you increase the diameter by 33%, you now have a larger sphere. You're going to find the volume of each of them, the original one, which we already have here. It's that 3053. So find the volume of your new larger sphere and find the percent of increase, which is the difference of the volumes divided by the original, which, remember, the original is the volume before any increasing, which is that 3053. Okay? And that is how you get the answer to that one. Next, math exploration with polyaminos. All the polyaminos that I use in that last question, the polyamino question, turns out there are 21 of them total. Okay, one monomino, which means that it's just a single block, prefix mono. One domino, which is a polyomino made with 2 blocks. And I want to note here that when you're writing out all the different possible polyominoes, you can't rotate or flip or turn. So my domino here, you see there's only one. I would not go to my next grid and make a second domino just by turning my first one. No, it's still like a 2x1 shape. You've just turned it. That doesn't make a second domino. So really watch that carefully, okay? There are 2 trominos. Your 3 blocks could all be in a row, or a second tromino, which is made with 3 blocks there, okay? You can have 2 in a row and 1 on top. And again, you can't rotate that or flip that to make a third tromino. There are only 2, and there they are, okay? I'm going to do the rest of these in red so it shows up a little bit clearer here. There are 5 tetrominoes. Ever wonder why Tetris is called Tetris? Because it uses tetrominoes, and there are 5 of them. You've got your 4 blocks in a row here. You've got 3 blocks in a row with 1 on an end. You've got 3 blocks in a row with 1 in the middle. And again, see how I'm kind of using logic here to write these out? I started with my 4 blocks in a row. Now I move to all my tetrominoes I can make with 3 in a row. I can put that extra block up on an end. I can put that extra block in the middle. This would not be another tetramino because it's still just 3 in a row with a block on an end. I already did that one here. Okay, I just flipped it to get this one I just drew down in the second row. You can't do that. Okay, so this would not be a fourth one. We've exhausted all of our possibilities for 3 in a row. So now I go to 2 in a row, and I can have 2 in a row with 2 up on top, or I could have 2 in a row with 1 on the top and 1 on the bottom. And those are the 5 tetraminos that can be made. Your job now is to make the 12 pentaminos. There are 12 grids left, 12 pentaminos, which are figures made with 5 blocks. And again, I recommend kind of going through this logically here. Your first one could be 5 in a row. And then what can you make with 4 in a row? Well, you can put 4 in a row with 1 on an end. You can do 4 in a row with it more in the middle. Okay, what are all different things you can do, right? So you're making all the pentaminos there. And then finally, this last piece here says, obviously, it's pretty fun to see all the different designs and objects you can create with polyaminos. Are you able to arrange all 21 polyaminos above to make one full rectangle? So one complete rectangle, completely filled in, no empty boxes in there anywhere, a complete full rectangle using all 21 pentaminos. If you can, what are the dimensions of that rectangle going to be? If you can't, explain why. Why is it impossible to do so? Okay, that is your math exploration. Then we go to our mean median mode. Similar to how I had you track your sleep a couple packets ago, I'm now having you track your screen time. Okay, so for 7 consecutive days, which if you haven't started yet, you want to do that this weekend for sure. I want you to track the amount of minutes, notice the unit, minutes spent on the phone, tablet, computer, and TV. Okay, the biggest questions that came up, does your school device count as computer time? The answer is yes. Okay, and you're like, well, I don't know how much time I spend on my computer in a day. Okay, I can't keep track of that. Well, you don't have to be down to the minute necessarily. If you take a quiz in science and it's on the computer and it takes you, most of the period, almost all of the period, you can say that you took 45 minutes because that's how long the period is, or 50 if that's how long the period is, or maybe you finished a little bit early, it was more like 40 minutes. Okay, so you can round a little bit there. But don't just like round up to the nearest hour. If you spend 50 minutes, don't round up to an hour. Write down 50. Okay. What if I'm playing video games? What does that count as? Well, are you playing them on your computer? Count it for the computer. Are you playing them on your TV? Are you watching? Looking at the TV while you're playing? Then count it for that. Are you doing a switch situation where you're looking at a handheld tablet type of thing? That would be tablet time. Right? But all your TikTok time, all the time that you're watching videos and YouTubing and all that stuff on your phone, that'd be phone time there. And then your question here is, on average, what percentage of each day do you spend using screen time? So you're going to take the mean for each device, and you're going to add them all together, because what that represents is, on average, the total amount of screen time you have in a day. So take your means, add them all together. Let's say you get 12 hours, even though that's in minutes, it works out to be 12 hours. You take 12 divided by 24, how many hours are in a day? And that would be 50% of your day, spent on in front of a screen. And that would be your answer there. Okay, but remember, I want your units to be in minutes. And then finally, we have the polyomino question. You might be able to get some answers for those for the pentaminos by looking at what I have here. But where in the large figure does each individual polyomino fit? Identify them and put them in their place. And that's math packet number 7. That about wraps that up. If you turn in early, I highly recommend it. I'll get it back to you as quickly as possible so that if you have any issues, you can correct them before it is due on the 16th. But thanks for watching. Have a great day. Hope this helps. I'll talk to you later. Bye.